Hi, this is Engineer Spock from engineerspock.com, and I'll be leading you through the course. I've been working with the .NET platform since 2003. I've been professionally architecting and implementing software for nearly 7 years, primarily based on the .NET platform. I'm passionate about building rich and powerful applications using modern technologies. I'm a certified specialist in Windows applications and service communication applications by Microsoft. I am one of the coordinators of the MSK.NET user group in Moscow. And here is my teaching approach. No fluff, no ranting, no beating the air, I steam your time. The course material is succinct yet comprehensive. All the important concepts are covered. Particularly important topics are covered in depth. For absolute beginners, I offer my help on Skype absolutely free if requested. Take this course and you'll be satisfied. Build a solid foundation in software architecture, applying dependency injection with IoC-Containers. In many of my courses, I use techniques of dependency injection, and each time students write me private messages saying that they don't understand what it is, and thus they don't understand what's going on in the course I teach. This is very unfortunate from the learning perspectives. That's why I decided to create a separate video course dedicated to dependency injection, or DI in short. Dependency injection is the set of techniques that allow to supply dependencies to objects. Actually, if you have ever passed dependencies via constructors, then you apply the so-called constructor injection. Dependency injection is simple and difficult at the same time. On one hand, DI is comprised of simple techniques, and on the other hand, when we need to bring DI to the next level, we need to make things more complicated using the so-called DI or IoC containers. These are frameworks which perform dependency injection automatically. You just need to set one up in the application root, an extremely important notion which you'll learn about in the course, and after that it will resolve all the dependencies it knows about in the runtime. If you still don't understand what I am talking about, just believe me, you absolutely need to know about dependency injection. This course will tremendously improve your understanding of how software architectures emerge. So this course is must-watch for anyone who still don't understand what is DI and IoC containers. This course is aimed at all kind of developers. However, solid C# experience is required. The course provides solid theoretical base reinforced by practical material. So, for now the course covers Introduction to Inversion of Control, including Dependency Inversion Principle, or DIP, Inversion of Control, or IoC, Dependency Injection, DI in short, Dependencies and their types, what is pure DI and IoC containers, and what is Service Locator. The architectural implications of dependency injection. We will talk about DI-related anti-patterns and refactorings, including control freak, hidden dependencies, temporal coupling, constructor over-injection and how to avoid it. We will talk about ambient context design pattern, facade service, property injection versus bastard injection, and cyclic dependencies. Refactoring of an existing codebase applying dependency injection. We will talk about how to reap the fruits of DI. After that, we will take a look at DI containers, including overview of DI containers, the Unity DI container, late binding with Unity, what is aspect-oriented programming, or AOP in short, interception versus pure DI versus AOP tools, and some other topics. And we will also look at how to set up a bootstrapper with Unity, AutoFac, and Castle Windsor IoC containers. Great! I hope to see you inside the course. Enroll and learn what is dependency injection and how to apply it properly. This lecture is titled Definition of DIP. The dependency inversion principle is all about decoupling. This is very important, so I'll remind you what coupling is. Coupling indicates how dependent modules are on the inner workings of each other. Tightly coupled modules rely extensively on the specific state of each other, sharing variables and many types. Loosely coupled modules are fairly independent. They have a few well-defined APIs and share a limited amount of or no data at all. So decoupling is what we strive to. It is the process of achieving loosely coupled modules. You can understand modules here both as classes or assemblies. The DIP is applicable at different levels, at the source code level and the binary level. If you look at Wikipedia, you'll see that low coupling is often a sign of a well-structured computer system and a good design, and when combined with high cohesion, supports the general goals of high readability and maintainability. Well said indeed. So, what is the formal definition? According to the Agile Principles, Patterns and Practices in C# by Uncle Bob, high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Seems like this is a definition with two levels. The first level concerns modules and the second concerns abstractions. This is a great definition, however, as always, it requires some further clarification since it's very hard to apply and practice such advices without seeing any practical examples. I want to show you a picture which demonstrates the DIP in real life. Given a lamp, socket, and a solder, a question arises. Would you solder a lamp directly to the electrical wiring in a wall? If you do that, you'd be able only to use that socket for that lamp, because they are, so to speak, tightly coupled. To fix the problem, we need to come out with a standard plug, which you can see on the right small picture. If all the devices implement such a plug, then they can be plugged into the socket. The same is true for dependencies in code. The high-level policies should not directly depend on low-level details. In case of our picture, devices are not directly depend on sockets. You can find an exception from almost all the rules, so look at this picture. This is a cheap hotel where the hair dryer is wired to the socket directly. But in this case, this is done intentionally, and actually it is meaningful. The intention in this case is to defend the dryer from thieves. Again, this is a rare case. In this lecture, we mentioned the notion of a dependency. In the next lecture, we will look at dependencies more closely. This lecture is titled Dependencies. Let's define what we mean by a dependency. There are several types of dependencies: on a framework, on third-party libs, external systems like file system, database, or any system resource, and so on. Dependency on a custom type built on top of the .NET framework. In this section, the most important type of dependencies for us is the dependencies on custom types which are developed by us. For example, here on the slide, the person class depends on person repository class. Person can't provide its features without relying on the person repository class. The person repository is a low-level class which interoperates with a database, while the person is the high-level domain object. So, in this particular case, a high-level object depends on a low-level object. Such a case is aligned with how beginners build software traditionally. This is a high-level view on a classic application with 3 tiers. On the top, we have a user interface. A user interface calls API of objects which implement business logic. Objects which implement business logic call the API of low-level infrastructural objects which implement interoperation with a database, external web service, and so on. What's wrong with the relationships between layers on this diagram? Do you know what it is? The problem is that high-level objects of the domain layer directly depend on low-level objects of the infrastructural layer. The lamp is soldered to the socket like a vise. What would you do if a requirement to change the database management system comes into play? It's hard as hell to replace a dependency if there is a tight coupling between the dependencies. The most frequently changing parts reside on boundaries of a system. User interface and DB-related stuff are irrelevant from the domain perspective. So, the domain logic should be independent of irrelevant things. To fix the problem, we need to revert the dependency which points towards the infrastructural layer. On this example, I'll show you how we can decouple one abstraction from another. A fundamental theorem of software engineering states that we can solve any problem by introducing an extra level of indirection. So let's do exactly that to decouple person from the repository. Here's the slide which reflects the changes made by simple refactoring. We often refer to such interfaces as to seams. These seams allow us to inject any dependency we want, which of course implements that interface. This is a simple yet powerful technique to invert the dependencies, achieving a low coupling between components. Another interesting aspect concerns runtime and compile time dependencies. Look at the diagram. Here we have a module A that calls function f on module B through the interface. When we use polymorphism creating an interface, inserting it between module A and module B, we end up with that module A has a runtime dependency on B, but it doesn't have a compile dependency on it. We can compile just module A if we want to, without recompilation of module B. In languages like C++, it helps to significantly reduce the amount of compilation time. That was the basics of what the dependencies are. In the next lecture, we'll take a closer look at two major types of dependencies. This lecture is titled Volatile and Stable Dependencies. In the previous lecture, you saw on a simple example how to invert the dependency on a repository by introducing a layer of indirection. A logical question which comes to mind concerns what dependencies should we abstract away? And to answer this question, the first thing we need to do is to realize that all the dependencies can be divided into two camps: volatile and stable dependencies. Let's define volatile, or in another word, unstable dependencies. According to Mark Simon, a dependency should be considered volatile if any of the following criteria is true. The dependency itself depends on the environment, forcing the caller to set up that environment. A classic example would be a dependency on a database, or any types that imply interoperation with a database. Any other external systems like web servers also fall into this category. The dependency doesn't yet exist and is still under development. This is a regular deal when we want to write code which, among other things, interoperate with an object inexistent at this point. We don't want to wait that object to be written, so we just introduce a seam which reflects the API of that object and make calls through that seam. The dependency which is not installed on all machines of developers. And the dependency has a non-deterministic behavior. It can depend on datetime now, random numbers generation, and similar unstable by their nature things. In general, we can define stable dependencies as dependencies that are not volatile. It may sound odd, but it's quite simple and useful. so we will stick with that definition. Volatile dependencies are those which we want to abstract away by introducing levels of indirection. Since they are unstable, we at least need to have a way to replace them by test doubles in unit tests. Otherwise, we may end up with untestable application. Remember that you can't treat an application testable until its design allows to write unit tests. If an application allows only integration tests, it should be considered untestable. Let's elaborate the topic of DIP by learning very close terms IOC and DI. We will talk about them in the next lecture. This lecture is titled Definitions of IOC and DI. In the lecture where we discussed the notion of dependencies, we saw this diagram. If you look more closely, you will notice that module A has a relationship of composition with the interface. It means that we need to inject the module B as the implementer of that interface somehow. This example demonstrates what is dependency injection. Dependency injection is one of the most important notions we will use throughout this section, so let's separate dependency injection and dependency inversion principle to avoid misunderstanding of these closely related to each other concepts. There is actually another general term, inversion of control, and you also should understand the difference between this term and the previous two we talked about. So let's give definitions to these terms. And we will start from the IOC. Inversion of control is a very general term which reflects the model of relationships between a caller and a callee. A classic flow of control implies that a client has a full control over the environment and sequence of calls to library methods. The inversion of control implies that a callee, we can imply any library methods when we say callee, take the control over some calls between the caller and the callee. The simplest form of inversion of control is callbacks. The main idea of a callback is to provide a way for a callee to call a caller back. So that's why there is a very important difference between regular libraries and frameworks. Frameworks rule the client code. Frameworks provide plugs which have to be just filled by clients. Frameworks also have the control over the environment. This is the inversion of control in action. Dependency inversion principle is a more detailed version of the inversion of control notion. DIP concretizes that high-level modules should not depend on low-level modules, and so on. Inversion of control is a meta-principle in a sense. According to the definition of the dependency injection given by Mark Simon in his book Dependency Injection in .NET, which I recommend to you very much, dependency injection is a set of software design principles and patterns that enable us to develop loosely coupled code. At the same time, you need to understand that IOC can exist without DI. IOC is possible without DI because we can change implementation by relying on subclassing, for example, by applying the template pattern, which was discussed earlier. Nevertheless, the main way to perform the inversion of control is to apply dependency injection techniques. In the next lecture, you'll see an example of DIP violation. Here's a simple demo which demonstrates the essence of a problem. In this case, we have a class named Divergence Checker, and here's what it does. We have two physical devices which are represented by two classes, a counter and fiscal registrator. This is a case from my practice. In Russia, when we sell anything, we need to register the selling operation in a special device called fiscal registrator. In my case, we have a separate device which performs encrypting and decrypting operations and unfortunately has to double the responsibility of a fiscal registrator, keeping all the details about sales in safety. As a consequence, we need to periodically check that there is no divergence between counters of a physical registrator and that special device represented here by the counter class. To perform that check, I implemented this class. Right now, this class logically has two dependencies. It depends on a counter and physical registrator. These classes directly talk to physical devices. In the real world, the gain divergence checker exposed more than one public method, but in this case it's enough to have the only one. This method actually checks if there is a divergence between counters of two devices. This method uses both dependencies. It takes two counters from one device and logically same counters from another device. Then it just checks if corresponding values are equal. Let's say we want to write a unit test for the hasDivergence method. How are we going to do this? With the current design, there is no way to write a unit test. The gainDivergence checker class is tightly coupled to the counter and physical registrator. These dependencies are unstable or volatile, since they represent real physical devices. Physical devices are always inclined to unstable behavior. That's why we can't write trustworthy unit tests. In the next lecture, we will look at 3 ways of applying dependency injection to fix the problem. The root cause of the untestable design in this case is that this class is dishonest. It lies to its clients. It lies about the fact that it has 2 dependencies. It lies by hiding them. The obvious way to fix the problem is to make dependencies visible. There are 3 major ways to accomplish that: constructor injection, property injection, and method injection. Constructor injection is when we request dependencies to be passed via the constructor. So the obvious refactoring can be done as this. The first thing we need to do is to create a seam which will serve as a boundary between domain logic and external devices. Now we can continue our refactoring process. Now, a client can't create the gainDivergence checker without thinking of dependencies. A client sees them and has to decide what to pass in. The responsibility is shifted to the client's side, and this is good. Now we can write a unit test replacing these dependencies by test doubles, which are under the full control of a client's code. Before writing a unit test, look at the other 2 options: property injection and method injection. Firstly, let's look at how code will look like with a property injection. The difference between this option and the previous one is that the client's code can reset the dependency whenever it likes. At the same time, from the API perspective, a client now can create the gainDivergence checker and forget to set the dependencies. After that, it can call the hasDivergence method and face the null reference exception. It means that the encapsulation of this class is broken. It doesn't provide guarantees that its methods will work as expected. Another option is to request the dependencies in the method where they are needed. It may look like a little bit weird, but it is absolutely valid option. In this case, the client's code will be unaware of any dependencies until it calls the method. This design preserves the encapsulation. It provides guarantees that the hasDivergence method works as expected in any cases. Let's write a unit test which validates the correctness of the hasDivergence method. Great! The test passes. In this lecture, you've seen a simple example of applying the dependency injection techniques. They're indeed really simple. In larger examples, the techniques will remain the same. Before continuing, I want to give a summary of the 3 DI techniques we just applied in the next lecture. This lecture is titled DI Techniques. Constructor injection implies that dependencies are going to be passed in via constructor. The most beneficial aspect of constructor injection is that it protects the invariance of the object. The object once created will always be in a valid state. However, you should be aware of the following possible pitfalls. In large systems, constructor injection tends to accumulate many dependencies. You may see more than 3 dependencies requested via a constructor. However, this is not the drawback of the constructor injection itself. Most likely, this is a smell of violating the SRP. In case a constructor requires more than 3 or 4 dependencies to be passed in, consider the possibility to extract any responsibilities into separate classes. Sometimes it happens that several dependencies tend to be passed in together. Here's a code snippet which shows that a view model takes 4 dependencies, and imagine that many other view models take the same dependencies as well. In such cases, it would be wise to create a container object for them and require that container's object to be passed in the constructors. Seems like it has no effect, but it is always a good idea to join objects which go together in many cases. One day you'll want to introduce a custom validation method which is related to all the dependencies or something like this. However, most likely more than 4 parameters is the smell of the SRP violation, as I said. So take a closer look at the responsibilities of a class which requires so many dependencies. Another interesting case concerns the, so to speak, non-obligatory dependencies like a logger. It's a valid solution to expose several constructors, some of which set the default implementations of the dependencies. You can see here an example. In this case, you may replace in the unit test the iLogger by a dummy test double, which does nothing, while in the production code clients can just use the default constructor, since in the majority of cases no one cares about the logging mechanisms. Another pitfall you may stumble upon is that such frameworks like the Entity Framework or other object relational mappers may require from objects to have a public default constructor. In such a case, you'll be forced to expose a public default constructor. Otherwise, you'll get an exception in the runtime. Of course, you can consider writing a wrapper around such an object which stands very close to a boundary of a system, thus preserving the encapsulation. If a certain dependency is used only in a single method, then consider removing that dependency from the constructor and request it as an argument of that method, which certainly needs it and can't provide its service without it. In other words, consider to use the method injection. Property injection implies exposing the dependencies via properties with public setters. It allows to replace the dependency during the entire lifetime of the object. The flexibility is the main advantage in this case. However, the drawbacks are so heavy that we should strive to rely on this way of injecting only in case of non-obligatory dependencies such as loggers. In such cases, there should always be a default implementation of that dependency and it should be set in a default constructor or right in the property. You see the example on the slide. This code in addition relies on the C#6 feature of property initialization. In any other cases, you should avoid property injection since it easily can break the encapsulation of a class and make the dependencies hidden. Dependencies exposed as properties are hidden because no one is obliged to remember all the internal details of a class. Method injection is an interesting technique. Dependencies which are set via properties or constructors are usually used by many methods throughout the lifetime of the object. However, sometimes an implementation may vary from one call to another call, or if a method is static. For example, the conversion of one currency to another requires an object which gets the rate. A similar example is the iFormat provider, which is required in such methods like double parse. However, think twice before implementing method injection. If you want to pass a dependency directly to a method just because only that method among 20 other methods uses that dependency, then this is a smell of SRP violation. Maybe a separate responsibility is hiding inside of that class. Another problem with this approach is that IoC containers can't automatically inject the dependencies to methods. IoC containers are tools which help to automate the process of dependency injection, and we will discuss it further in this section. Okay, now we got the idea of dependency injection and three major techniques. These simple techniques have fundamental implications. Of course, in the real life, things can be slightly harder than we saw in this lecture. The problems appear at the architectural level. Let's talk about architectural implications of the inversion of control and dependency injection in the next lecture. This lecture is titled Architectural Implications. Inverting dependencies is the means by which we create boundaries between software modules. When we want to create a boundary, we choose which dependencies to invert against the flow of control, so all of them point in the same direction across the boundary. Boundaries like on this slide are the way we create plugins. A plugin is a module that is anonymously called by another module. In other words, the caller has no idea who or what it is calling. In this case, the module A doesn't know it calls the module B. Plugins can be deployed independently, and moreover, they are independently developable. We divide the system by boundaries and then invert the dependencies that cross those boundaries. So plugins define the boundaries of your system. The old model of building software systems with three tiers is the data-centric model. In such architectures, the database and its schema is the center of the system. It drives all the other parts of the system. Frankly speaking, this approach is still alive and sometimes could be beneficial, but nowadays we're inclined to treat databases and UI as tools which can be replaced. In data-centric architectures, a significant part of domain logic is going to be implemented at the database side, so it will be implemented in stored procedures with a language like SQL. The major problem with this approach is that data processing related languages like SQL, which are very efficient in processing of tuples, were not designed to implement business logic, at least significant chunks of business logic. Database-related languages are very poor on features which allow to model relationships between domain objects. This is one of the major reasons why the worldwide community of developers shifted to another approach where the database is treated as a low-level detail. And here we reach the point when we continue to analyze the implications of the architecture based on plugins. Here is a diagram where the domain is in the center. When we treat database and UI as tools which are mostly irrelevant, we come up with the idea that the core of any application is the domain logic. Domain logic is the most stable part of the system, since domain policies change relatively rare. For example, the UI part changes far more frequently. Notice that all the dependencies point towards the domain. If you enlarge this diagram, assuming that these big layers are comprised of many objects, you'll get the following diagram. I've got this diagram right from the blog of Mark Seaman. Notice that all the dependencies still point toward the center of an application. If you add the layers to this diagram, you will end up with the following. This diagram depicts what architectures call onion architecture. There are other similar notions such as hexagonal architecture and ports and adapters architecture. All these terms mean essentially the same, they are all about the same. Ports are those scenes we introduce by extracting interfaces, and adapters are plugins which come from the boundary of a system. In large systems, the graph of dependencies is very large, though you should strive to keep the graph as flatter as you can. Even if you keep the graph flat, you also can face the problem of controlling the lifetime of dependencies. This leads to an interesting question. Who is responsible for keeping the control over the dependencies' instantiation and their lifetime? And the answer is obvious. Any application starts from the main method. Developers often refer to main as not to a physical entry point, but as to an infrastructural point where all the relationships between dependencies should be set up. The idea of setting up all the dependencies in a single place in main actually conforms to the single choice principle that was discussed in the OCP section. Main is the single place which knows everything about dependencies and their relationships. It doesn't necessarily mean that all the dependencies will be instantiated in main. Some of them may be instantiated in main indeed. The other will be automatically created in the runtime according to the setup made in the main partition. In this lecture, we figured out that the main is the infrastructural point where we set up all the dependencies. Now we need to understand how to set up them in practice. In the next lecture, we will look more closely at PureDI and IoC-Containers. They are related to two major techniques which allow to set up the dependencies and inject them properly. This lecture is titled Common Smells of DIP Violation. All the common smells of DIP violation take their roots from the DIP definition. DIP clearly states that high-level policies should not depend on low-level details, so the common smells are the following. A class explicitly creates one or more dependencies, hiding them from a client. A class uses non-deterministic dependencies like date, time, or random. There are ways to decouple such dependencies, which often come from the .NET framework itself. One way is to create a class which works with non-deterministic dependencies and cover it by integration tests, and another option is to create some kind of adapter. I mean, create your own interface and implement it in a custom class which uses non-deterministic dependencies. Then you can use that custom interface in the production code and replace it by test doubles which are under your control in unit tests. A class uses static dependencies, very often they are singletons. Singletons make unit testing very difficult. Static dependencies of a class are also hidden from a client, so if a static dependency was not properly instantiated, then a class will most likely behave itself incorrectly, throwing exceptions and so on. This forces clients to remember about hidden dependencies all the time. This is almost always a bad thing. The main idea of removing the DIP smells is that you need to extract a layer of indirection and make the class which violates the DIP dependent on that layer of indirection. Another principle which often helps is the single responsibility principle. Adhering to the SRP often helps to avoid extracting of useless interfaces. In the next lecture, we will summarize what we learned in this section. This lecture is titled Conclusion. In this section, you learned: what is DIP? DIP implies that high-level policies should not depend on low-level details. That there are two major types of dependencies, stable and unstable, or volatile. Unstable dependencies are those to which we won't apply the inversion of control. What inversion of control and dependency injection are, and how these notions are related to the DIP and to each other. Three techniques of dependency injection: constructor injection, which should be used in 95% of cases, and property and method injection. That adhering to the DIP leads to a plugin architecture, which is commonly referred to as the ports and adapters architecture. This led us to a conclusion that there should be a single place which knows everything about application dependencies and their relationships, and this place is main. You also learned that manual dependency injection may become tedious, and that's why IoC-Containers exist, which helps to simplify dependency injection in difficult cases. You learned how to build a simple IoC container. And you saw an example of a real-world application which relies on an IoC container and sets it up in main. And we also summarized what the common smells of the DIP violation exist and how to fix them. This section is the last one in this volume, which covers the last principle of the SOLID acronym. In the next volume, we will discuss the meta principles and how they are related to SOLID principles. I'll be waiting for you in the next section. Thank you for watching.